All right, so this next segment of questions deals with Newton's laws. And there's a question that says define his three laws. And again, the more important thing is to be able to use his three laws, to really understand them. So his first law is the law of inertia. Remember, inertia is not a force. Inertia is the tendency of an object at rest to stay at rest, or an object in motion to continue with constant speed in a straight line. It's just that natural tendency of all objects. As Bill Nye says, inertia is a property of matter. It's not a force, it's just that tendency of all matter. And of course, Galileo was studying that in order to convince people that the Earth could be moving for no other reason than it was already moving. So the idea of inertia. So law of inertia. Inertia, again, that's Newton's definition. An object at rest will stay at rest, or an object in motion will continue with constant speed in a straight line unless acted upon by an unbalanced force. That's that unbalanced force we've been talking about in the second law. Another definition of inertia is that it's a resistance to a change in an object's motion. An object at rest tends to stay at rest. Again, it's a resistance to a change in its motion. Inertia is measured by mass. So an object's mass is a measure of its inertia. The greater the mass, the greater its inertia. When you talk about horizontal motion on the Earth, where gravity acts, and you have to stop something like catch it with a glove, you stop it, you are stopping the object's mass. Remember, weight is downwards. When you're applying a force to decelerate a mass, that's all about inertia. When you're holding on to something's weight, that's all about weight and force. But when you are decelerating a mass, that's all about inertia. And if you are out in outer space where something is weightless, then it's not about weight, obviously. But you have to catch something, or something hits your head or whatever. You have to apply a force to decelerate the mass. It's all about inertia. All right, about that property of matter. It's not about weight. So Newton's second law, of course, is net force equals mass times acceleration, or acceleration is equal to net force over mass. So another way to write this, remember, is acceleration equals net force over mass. And so if you double or triple the net force, you'll double or triple the acceleration. But acceleration is inversely proportional to an object's mass. So if you keep the force constant, but you double the mass, you'd have half the acceleration, right? They're inversely proportional. If you triple the mass, you would have 1/3 the acceleration. Acceleration and mass are inversely proportional, keeping the net force constant, like I said. So that's Newton's first two laws. His third law, of course, is his law of action-reaction. All right, and remember that all forces occur in pairs. The tricky part's identifying the paired force. If you're talking about the weight of an object and I ask you for its pair, don't call it weight. Be more specific in identify the two objects that are gravitationally attracting each other. Then it's not so hard. You know, the paired force to the weight of the marker. Think of it this way. What is the weight of the marker? It's the Earth gravitationally pulling down on the marker. Flip that around, and its pair is the marker gravitationally pulling up on the Earth. You push open the door. The paired force to that is the door pushing back on you, all right? It's that interaction between you and the door, okay? You sit on your chair, all right? You are pushing down on the chair, and the chair is pushing up on you. That's a type of normal force. Those are two paired forces. They represent the same interaction. They'll always have the same value. All right, let's look at some of these questions. Let's see, what would be the acceleration of the block? This is question well, it depends on whether you're AP or honors. And yeah, this is the one with this right here. Okay, what would be the acceleration of the block if the surface were frictionless? And so if it were frictionless, then the net force is 50, because that's the only force in the horizontal axis. There's no acceleration vertically. And so the net force would be 50. And if that's 50 and that's 25, notice I kept the numbers easy. 50 divided by 25, divide by mass over here. All right. And you would get, what, 2 meters per second squared, right? Assume the block travels to the left with constant velocity over a surface with some friction. Constant velocity, so not accelerating, constant velocity. Determine the magnitude of the frictional force and the coefficient of kinetic friction. Well, if it's constant velocity, then there must be friction in the opposite direction, so the applied force would equal the friction. They balance each other out. It's sliding that way with constant velocity. The two forces would balance, so the frictional force would be 50 newtons. The coefficient of kinetic friction, remember, is you only have one equation for kinetic friction, and that's mu, that's a mu, times the normal force. And so solving for this, it's going to be kinetic friction, which we just said was 50. The kinetic friction would be equal and opposite to that, all over the normal force. If you draw a force diagram, well, I love them so, you'd have the weight down here, you have the normal force up here, you have the applied force that way, and you have the kinetic friction that way. Okay, so this, I'm just going to go ahead and use 10. I mentioned, I asked you on these questions to use 10 instead of 9.8, and my answers will be based on 10. So if that's 25 kilograms, then the weight would be 250 newtons. And then in the net force, y-axis, the forces are balanced, so this must be 250 newtons. Again, if this is 50 newtons, then this must be 50 newtons. Therefore, coefficient of friction is going to be the 50 newtons divided by 250, which is, what, 0.2, I believe? Yeah, 0.2. It has no units, it has no sign, it's just 0.2. So the coefficient of kinetic friction would be 0.2. What would happen to the acceleration if the mass were tripled but the force stayed the same? Okay, so if that goes up by 3, that would be 1/3 the original. Again, if this were doubled, that would be 1/2 of the original acceleration. If the mass were tripled, you'd have 1/3 the original acceleration. If you had 4 times the mass, then your acceleration would be 1/4 the original acceleration. Okay, whatever you did, keeping the force constant, if it's just divided by m, you get a. If it's divided by 2m, you get half of that original acceleration. Divided by 3m, you get 1/3. If you have 5 times the original mass, you'd have 1/5 the acceleration of just a single mass. That's what I'm testing for there. And what would happen to the acceleration if both the mass and the applied force were tripled? Well, if you triple the numerator and triple the denominator, nothing happens to the acceleration. For those of you that did that experiment, the honors folks did this, the AP folks did not, where you had a cart and you just let the cart roll down the hill, and then you doubled the mass of the cart, let it roll down the hill, tripled the mass of the cart, let it roll down the hill, quadrupled the mass of the cart, let it roll down the hill, and then quintupled the mass of the cart, let it roll down the hill. And each time we measured the acceleration, in that case, the acceleration was unchanged, because when we doubled the mass of the cart, we doubled the FGX acting on it, right? Because FGX is weight times the sine of the angle. The angle didn't change. And so we doubled the mass, we doubled the weight, so we doubled FGX. When we tripled the mass, we tripled FGX. When we quadrupled the mass, we quadrupled FGX. When we quintupled the mass, we quintupled FGX. And so we're multiplying the denominator and numerator by the same factor, and the acceleration remained unchanged in that case. Okay, so there's that. I think that's, here's this last question. You pull a box up a ramp with an applied force of 200 newtons. You pull a box up a ramp. Let's just use this. With an applied force of 200 newtons. So 200 newtons. Come back here. Let's see here. The box accelerates up the ramp. It's accelerating up the ramp. It's accelerating, not just moving, but accelerating up the ramp. Speeding up the ramp. Describe the magnitude and direction of the force of the box pulling back on you. Well, if you have the force, if it's 200 newtons, the force of you pulling, that's Y for you, pulling the box, YB, you on box, all right, is 200 newtons up, that's that one, then how much is the box pulling back on you as it accelerates up the hill? Well, it's got to be equal and opposite to that. So if you pull the box upwards, force of you on the box is 200 newtons upwards, then the box pulling back on you must be 200 newtons down the hill, all right? Has to be. If you pull it up with 200 newtons, it's pulling down on you with 200 newtons. It can still accelerate, right? That's the thing where people really get confused. They think, how can it accelerate, right? It accelerates because you're pulling up on it with 200 newtons, and as long as that's greater than FGX and any friction, it's going to accelerate up the hill, right? This arrow here, the force of the box pulling back on you, box on you, B-U, B-Y, box, that's got nothing to do with the box itself. It has to do with you, right? So it wouldn't go in the box's force diagram. So again, the answer to that one, if you pull a box up a ramp with an applied force of 200 newtons, the magnitude and direction of the force of the box pulling back on you is going to be the exact same number no matter what, in the exact opposite direction. No matter what, accelerating or not accelerating, constant speed, not constant speed, at rest, not constant, not at rest. Always going to be the same number in the opposite direction. Always, always, always. That's the essence of Newton's third law. All right? Well, that was indeed fun.